This episode is sponsored by Brilliant. Black holes are amongst the most dangerous and destructive things in the universe, so let's go live on one. So today, we return to the Outward Bound series to look at colonizing black holes. We talk fairly often on this channel about advanced civilizations using black holes in various ways, but we're usually talking either about artificial micro-black holes that emit Hawking radiation and need to be fed constantly so they don't disappear, or about civilizations so far forward in time that black holes would be prevalent, while what we call stars would be ancient history, part of a brief, bright era when the universe was still settling down from the Big Bang. But today, we are going to talk about how and why black holes might become the preferred place for much nearer future civilizations to colonize, even while stars still burn and uninhabited planets are abundant. In a lot of science fiction, a ship stumbling across a black hole is cause for panic. But in reality, the crew would probably be popping the corks on the champagne because that's some very valuable real estate they just found. To understand why, let's talk briefly about what our descendants would be looking for in a place to colonize. Stars are useful fundamentally as power sources. Earth is basically self-sufficient except for the light we receive from the sun, which keeps our planet comfortably warm and powers our entire ecosystem. But that power doesn't originate on the surface of the sun that we can see. That goes on deep down inside, where fusion turns hydrogen into helium and produces lots of lethal gamma rays. They get absorbed and re-radiated as lower energy, longer wavelength photons many times by the layers above, until that energy is eventually emitted at the surface, mostly as visible light and infrared in the case of our sun. Many of our colonization methods rely on collecting that light, and we discuss lots of ways to concentrate or diffuse that light to let us settle at distances of our choosing from the star. Other colonization plans involve replicating sunlight in our habitats using other energy sources. Fusing hydrogen into helium produces millions of times more energy than any chemical process does, but controlled contained fusion is still something that eludes us. We do achieve fusion in hydrogen bombs, which are often compared to the sun, but current hydrogen bombs require rare isotopes like deuterium, tritium, or lithium deuteride, the ones that are easiest to fuse. So a nice reactor you can dump common hydrogen into and get electricity from is quite a ways off, and it would still only release less than 1% of the energy available in matter, Einstein's E equals mc squared. Black holes are much easier and efficient. There are several ways to get power from a black hole, and which one you'd use depends on your level of technology and the size of the black hole. You can check out our video about black hole ships from a few weeks back if you'd like to learn more about those methods. But for black holes of the size we are discussing today, the size you would colonize, the easiest method is to simply drop matter in and collect the X-ray radiation pouring from the accretion disk. Matter in the accretion disk is compressed with such force and moving so fast that friction produces immense heat, which for an average natural-sized black hole would be radiated in the X-ray part of the spectrum. This is what we believe powers quasars, so a scaled-down version of the brightest objects in the universe would be the power plant of your colony. Black holes also have potentially enormous value for industrial uses, besides just being a great power source. They are the perfect way to dispose of anything you don't feel is safe or economical to recycle or otherwise safely dispose of, as a black hole doesn't care what kind of matter you feed it, just the amount. People often talk about dumping radioactive waste into the sun, which is not a great idea for reasons we'll save for another day. But in a black hole's case, it's actually a highly profitable way to dispose of dangerous material. As we discussed in black hole ships a few weeks back, These objects are also handy for space travelers because they allow you to change directions with minimum fuel. You can fly close to any massive body to alter your course or give yourself a little speed boost, but the sharper the turn you want to make, the closer the pass you'll have to make, which might be too close to the heat of a star, if not inside the star itself. And contrary to what's depicted in most sci-fi, you can fly closer to a black hole than you can to a star of equal mass, because it's much cooler and doesn't have all that pesky stellar atmosphere and solar wind that you'd rather not encounter at high speed. Though I'll note that black holes are not the only dead stars handy for space travel. When a star starts dying, it usually spends a fair amount of time as a red giant, and those are actually so thin you could run a ship through their atmosphere as a means of slowing down. Not our topic for today, but since slowing a ship down is one of the biggest issues with interstellar travel, these offer a partial solution. You can push on ships with lasers to accelerate them, but there will be no laser to slow you back down at an undeveloped destination, so that constrains how fast you can travel to uncolonized systems. Any fuel you have to save for deceleration at the end can't be used for acceleration along the way. Red giants might be ideal vanguard systems for colonization because you can reach them at higher speeds than other neighboring systems, letting you set up as the first port of call for that region of the galaxy. In this same way, black holes make good waypoints for distant places, as you can head in their direction and use them to alter your course and boost your speed, and they can also be used to slow down too. Indeed, one you can see a long way off is likely jetting relativistic matter off its poles, and you might be able to use conventional sails or magnetic sails to use that for braking drag or an added boost. So such places might naturally tend to be the first distant places we visit and settle, and once you've colonized it, assuming you've got some raw materials nearby, which is quite likely as even the supernova that produced it wouldn't have been powerful enough to destroy the original outer planets it probably had, you've got a giant power plant on hand and raw materials to feed it and build with. Initially, you wouldn't want to live too close, though again, not for fear of gravity. The method you're likely to use for power generation is to throw matter around a black hole to form an accretion disk, which emits huge amounts of X-ray radiation. So if you want to be close, you'll have to wrap that thing in radiation shielding, and to prevent any large chunks of matter falling in and producing big blasts of X-rays. Of course, if you're building a shield, you might want to throw some dirt on top of it. Dirt's good radiation shielding too, and we can add air and water and artificial lighting, and presto, new planet. Except it's kind of a huge one. Your typical stellar mass black hole is 1 million or more times as massive as Earth, so if you build a shell around it for normal Earth gravity, it would be a shell 1,000 times wider than Earth and 1 million times larger in surface area, a true mega-Earth. I should note it would also have an escape velocity 32 times higher than Earth's, 354 kilometers per second, instead of 11.2 kilometers per second. The gravity well is bigger and deeper, for all that the force on you is the same as on the surface of Earth. Easy to visit, but hard to leave, making it quite the tourist trap. Now the means for doing this shell is one we've discussed many times on this channel, and that's the orbital ring. Our episode on colonizing the Sun gives a full discussion of how to do that around a massive object, but basically, by creating a hollow loop of matter that does not orbit the planet or star or black hole beneath it, but merely wraps around it, then spinning another hoop or stream of matter inside it at faster than normal orbital speed, we get a big stationary ring we could walk around on. We could make many of them, cocooning that object with a mesh, and then presto, shell world. In this case, you'd probably have a lower shell from which to dump matter into the black hole and absorb the radiation to make power. You might have several habitable upper layers too. Such planets had to be very big because black holes are as massive as large stars, and since gravity increases with mass and falls off with distance, and you have to be a lot farther from a black hole than from Earth's center for the gravity to be walkable, As mentioned, black holes often gain mass or even merge with other black holes, as we often find black hole candidate stars, supergiants, growing up together in big clusters. So there are going to be some very large ones of hundreds or even thousands of solar masses. Shells around them work just fine too, but they get even harder to leave. Even though the gravity on that shell is presumably the same as Earth's surface, the escape velocity will keep rising. As you probably know, time slows down in bigger gravity wells, and this slowing can be approximated as the same as the escape velocity in terms of the classic special relativity effect of time slowing on a fast spaceship, at least when you're not too close to the event horizon. So a shell that had an escape velocity of 1% of light speed has the time running slower on it basically the same as a spaceship traveling at that speed, which in truth is very little. Your clock would only lose about 4 seconds a day, or about 26 minutes a year, and would require a mass of several thousand solar masses. Such black holes are not very common, though considerably larger ones reside at the cores of most galaxies. On our first example, the simple mega-Earth built around a black hole of a few solar masses, with an escape velocity of merely 354 kilometers per second, time would only be running about 22 seconds slow per year. But for those big galactic core black holes, often running into the millions of solar masses, a shell around those, what we call a Birch planet, running 1 trillion times the mass and surface area of Earth, would have an escape velocity 1,000 times that of Earth, about 4% of light speed, and you're losing over a minute every day. Still not a lot, but such an object is so huge that its tidal forces are tiny even where the gravity is high. So an object placed at 100 times the Earth's gravity, a tenth as far from the center as the planet shell, would actually be losing a few days a year. This can go way higher though, as black holes can be made much bigger. That monster at our galactic core of a few million solar masses is not even 1% of our galaxy's mass. It will only grow with time too. One which had swallowed up most of its galaxy's mass would be having an escape velocity around half the speed of light, and time running a good deal slower. And at this point, the spaghettification effect on matter near the event horizon is practically none. Those willing to experience higher gravity would experience much slower time. It also means you could drop down into that black hole without being killed in the process. Indeed, you could do this on a much smaller one too. We don't know what goes on down inside them, but the various options in this or that theory would include some that might make this a good idea, assuming you had no desire to return to the universe outside, which might indeed be the case by the time monster-sized black holes like this were the norm, as the universe would be petering out by then. On these very large ones though, where you are likely including multiple layers of shells, time would be running significantly faster or slower depending on which layer you resided, and would be much more extreme if you were in the higher gravity areas, if for instance your biology was adapted to a few Gs, or if you were post-biological and could endure hundreds or even thousands of Gs. We've explored those possibilities quite a bit in our Civilizations at the End of Time series, but for this episode, let's get back closer to the here and now. A question arises as to where you get these black holes from. It's worth keeping in mind that black holes aren't terribly common. Only around 1 in 1,000 stars that forms is massive enough to become a black hole, but that still means we ought to have at least 100 million of them in our galaxy now, with of course a supermassive one in the center, 30,000 light-years away. The closest one we know of, V616 Monoceros, is about 3,000 light-years away, with the famous Cygnus X1 being the second closest at 6,000 light-years away. But these are probably not the closest, only the closest known. While stars are not randomly placed by type, we have many stars massive enough to form a black hole closer than either of those, and those are just living ones. Remember, we said 1 in 1,000 that forms is big enough to die a black hole, but such stars live short lives, hence their rarity among our neighbors. They form and die after just a few million years, as opposed to their black hole remnants, which will live on for the next best thing to eternity. Although talking about these stars living briefly and dying as black holes, given the huge value of black holes, and other dead stars for that matter, seems an increasingly flawed definition. Even the name, black hole, contains two words that are both so pessimistic, and also both incorrect. It's like calling an island a dead volcanic eruption. Technically true, but a weird and short-sighted way to regard a potentially lush tropical isle that's far more amenable to being colonized than a typical erupting volcano. Anyway, by default, we'd expect there to be hundreds of black holes for every massive enough star we can see alive now, though of course quite a few might have merged with siblings into more massive black holes by now, or been ejected from the galaxy. That said, while the nearest we can see right now is 3,000 light-years away, there's a couple hundred million stars in that volume, so there's presumably a couple 100,000 black holes in that volume too. Probably somewhat fewer due to mergers, ejections, and the galaxy's supergiants not really being evenly distributed. There's around 15,000 stars within just 100 light-years of us, our targets for a nominal first wave of interstellar colonization, and it would be a bit surprising if there wasn't at least one black hole in that region. Black holes are obviously hard to see, since they are only detectable by either wobbling their binary companion, if they have one, or if they are sporting a significant accretion disk of matter falling into them and giving off huge amounts of radiation. They wouldn't sneak up on you though. They're hard to see hundreds of light years away, same as planets, but you know one was there from its gravitational effects long before you were close enough to be in any real danger. While we might be colonizing black holes in our stellar neighborhood in just 1,000 years or so, it's quite likely we'll be using them for colonization a lot sooner. We've discussed some ways of making black holes in the Black Hole Ships episode, and some require no particularly advanced technology, just a lot of infrastructure, which a growing interplanetary civilization a few centuries from now might have. Although the power requirements are far larger for making bigger black holes, the technical challenges are a lot smaller. We've talked a lot about Kugelblitz black holes, ones of relatively low mass and short lives that give off huge amounts of power by hawking radiation, but it might turn out we are limited to making ones no less massive initially than a fairly small asteroid. Of course, once they are large enough, you can jam matter into them. There is no longer a power requirement for making them bigger. Quite the reverse. You're generating huge amounts of power while you do it. If you effectively have a point-like object of huge mass, and even one of Earth's mass is only the size of a marble, you have a handy source of artificial gravity. You could drill a hole into Mars and drop one down of the right mass, and suddenly have Earth-like gravity on the surface. Mars is about half the diameter of Earth and about 11% of Earth's mass. For that radius, it would need to be about 28% of Earth's mass for Earth-like gravity. You'd presumably get that other 17% from one of our gas giants or the Sun. Transport would be no problem, since a black hole you're feeding matter into is easily adapted into a ship's drive as a power plant, as we discussed a few weeks back. Handily, while the gravity is now Earth-like, the escape velocity is still decently lower than Earth's, just 8 km per second, and orbital speeds would only be about 5 km per second, much handier for things like spaceplanes, which we'll be having an episode on next week. This trick works as well on Mercury or Venus or Pluto, or our own moon or any of the other moons, or for that matter small asteroids or artificial spherical habitats. One might argue it's a bit mass wasteful, but they are good power generators, and older ones used as starship drives that had grown in mass too much might get retired to serve as the cores of microplanets. We also only mostly want hydrogen and helium, the overwhelming majority of regular matter in this universe, for power generation in suns or artificial fusion reactors, but fusion power is redundant if you've got artificial black holes that are way more efficient. In terms of size, for such things, you've got limits for both the top and bottom, but it's very broad. Go too big, and a shell at normal Earth gravity would be dangerously close to the event horizon, or even in it, but that's way up at galactic mass. Go too small, and the black hole is emitting so much Hawking radiation that normal gravity would put you in a place too hot to live, but that's getting down to a planetary size parallel to a modest backyard. If you've seen the Rick and Morty episode where they go hide on a microplanet they can walk around, yes, that is possible with this technique. With one caveat. As mentioned, a black hole dumped into Mars to give it Earth normal gravity still leaves it with a lower escape velocity, still more than enough to hold an atmosphere, which is mostly about creating a stronger magnetosphere anyway, but that effect gets bigger as we get smaller. If your microplanet only has an escape velocity about the same as the root mean square speed of room temperature air, it's all going to leak away very quickly, so you'd still need to dome it over, which arguably removes half the appeal such a planet has over a classic rotating habitat where there's no natural sky. Of course, you could still have windows and skylights, and could walk around outside in a spacesuit with normal gravity. Now, a planet isn't going to keep its atmosphere just because its escape velocity is higher than the speed most air particles zip around at. It will still leak fast, it just won't blow off rapidly if you puncture the dome. But if you're curious, an asteroid about a dozen kilometers wide and about a millionth Earth's mass, with its artificial black hole in the basement, would have an escape velocity of about Mach 1, and could probably get away with fairly minimal airlocks for spaceports. There's some great examples of such worlds in Alastair Reynolds' Revenger series, where the black holes in these worlds get called swallowers. Amusingly, most readers apparently miss that all the spaceships traveling to various other worlds in that book via light sails are actually just roaming around a single solar system in a partial Dyson swarm. Probably unsurprisingly, most channel regulars here did not miss that. So you can fill all your moons and larger asteroids up with such black holes and get normal gravity, and grind the smaller asteroids up to make artificial shells or regular cylinder habitats. Very handy approach for mining an asteroid too, since you've got all the power you need for running your mining and manufacturing and launching. That is still a lot of mass, but again it's mostly hydrogen and helium, which we can't build out of, and which we wouldn't need for fusion. One big issue though, first, you are still using that mass for power, and once it's down in that black hole, you're not getting it back, unless you're willing to wait a long, long time, and longer the bigger it is. Even a black hole with only a millionth the Earth's mass, itself barely bigger than an atom, is going to live over 1 billion trillion times longer than our universe is old, which is actually fine if you want to be storing power for after the sun goes out, but it is a long-term investment to say the least, and bigger ones live way, way longer. We can cheat though. Instead of using a single one, we can jam several into the same spot, just far enough apart they don't merge. One of say 120 megatons would be coming due about the same time our sun burned out, while those you might want to use as a ship drive might leak out in thousands or millions of years. People often suggest the main currency of the future would be matter or energy, and micro black holes make great long-term bonds, since you can store power in them as a perfect battery for very long times with very little leakage. Makes them a great way to store your treasury, since a black hole is harder to break into than Fort Knox, or at least harder to break out from with your loot. One problem though, especially for smaller ones, is it's going to be hard not to generate power while you're fattening them up. You might wonder how that's a problem, but consider, if I'm making black holes for a space habitat market, and someone puts in an order for a 1 billion ton black hole to be delivered next month, if even 1% of that feed matter gets radiated away as energy while I'm doing this, that's a trillion joules of energy released, enough to illuminate Earth for an entire year, or power our current global economy for 20,000 years. And you need 6 trillion of those to make an Earth-sized shell world, or the equivalent land area of many smaller microplanets. That would also represent the entire sun's output for a few thousand years, I mean, that's exactly why these are such ideal power plants. Now, handy thing about a black hole is so long as you're aiming the feedstock right down its gullet, there's no energy splash, no accretion disk, etc. And that's viable for one of modest size, and of course we can always find a use for power. You can use it for accelerating spaceships away, or power transmutation to turn one element you have in abundance into another you want more of. Getting rid of heat is an issue, but you can be doing this in the outer solar system, even way out beyond the Kuiper belt, where swarms of such black hole factories would enjoy thousands of times more radiating area than in the inner system. It's also the ideal place for running all your interstellar shipping and colonization out from, since high-speed collisions are less of a concern far from your core civilization. So I could easily imagine an inner solar system with our classic planetary colonization and asteroid and cylinder habitats slowly forming a conventional Dyson swarm where, far out from the sun, a growing black hole-based economy was sent out and receiving interstellar ships and exporting black holes to the inner solar system to slowly replace or augment the more standard habitats and worlds there, each with little black holes in their basement serving as either a current power source or a long-term treasury for the end of the universe. Of course, the outer solar system is a great place to be putting a defense network for your inner system, as we discussed in Colonizing the Oort Cloud, and beyond supplying power for such defense stations, black holes can be terrifying weapons, but we'll get to that in a few weeks. So we were talking about black holes and escape velocity today, and how you could use them to alter your course or gain a speed boost. There's an excellent quiz on black holes in Brilliant's astronomy course, and their astronomy quizzes are a great way to expand your knowledge on that topic and get comfortable working with a lot of the core concepts we often build our discussions of our future out in the galaxy off of. Brilliant uses a mix of interactive visualizations and illustrated and animated problems in short quizzes to help you learn about topics like that, or how to slingshot a ship around a massive body that a dry textbook or lecture just doesn't do as well, and it lets you do it at your own pace from the comfort of your own home, but also as part of a learning community that you can talk with for help or discussion. The most important part of learning is keeping it fun and interesting, and they do a great job of that, from their interactive courses to their daily challenges, which help to stimulate your thinking and connect to expanded courses if one of those problems grabs your interest. Learning's best done every day, and those daily challenges are an excellent way to warm up the brain and introduce you to exciting new topics. If you'd like to learn more science, math, and computer science, go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can solve all the daily challenges in the archives and access every course. So we'll get to our upcoming schedule on YouTube in just a moment, but first, we have an upcoming bonus episode coming out that won't be on YouTube. I'm not sure if I've mentioned it before, but a little over a year ago, I was invited to join a digital creator community called Standard that had got founded by the creators of Kurzgesagt and CGP Grey shortly before that. It's principally other educational channels, and while we all love YouTube and aren't leaving it, their algorithm really isn't optimized with those kinds of shows in mind, and it often limits what we can do or try out so that YouTube's algorithms don't bury our video or our channel. So we created Nebula, a streaming video platform that we control, so we can use it to try new things, explore new formats, and share more behind-the-scenes content. To honor that rolling out, tomorrow we'll be premiering a look at the Paperclip Maximizer, the concept of a runaway artificial intelligence, and an idea called instrumental convergence, that even intelligences with very peculiar goals, like making paperclips, will often mimic goals and behaviors of creatures with different goals, like survival. Nebula is only $5 a month, going to the creators to fund new original content and to improve the service, which is brand new. But you can watch that episode and others from folks like Kurzgesagt and Real Engineering for free with a 7-day trial. Visit watchnebula.com and get a free 7-day trial to check out the Paperclip Maximizer, and stay tuned for all the great stuff we're working on for you. As mentioned, today's episode is part of a short series on black holes that we started a few weeks back with black hole ships, and we'll be continuing that in 3 weeks with weaponizing black holes, and we'll look at some of the awesome and downright terrifying ways these might be deployed in the far future. But next week, we'll be returning to the Upward Bound series to look at space planes, particularly the Skylon spacecraft, and ask what technologies we'd need to let you take off from your garage and fly straight to orbit, or to the moon or Mars, in your own personal spaceship. For alerts when those and other episodes come out, make sure to subscribe to the channel. We also have our monthly livestream Q&A coming up this weekend, Sunday, May 26th at 4 p.m. Eastern Time, and I hope to see you then. Until next time, thanks for watching, and have a great week.